Hell yeah. Oh yeah.
Okay, let's see if we are synchronized.
Mine's synchronized.
Let's
see
go.
about you. Yes, you're
It is.
synchronized.
Let's go. All right, we're ready. Whew.
Bro. Okay, I feel like this is gonna be really good for our setup later
Mhm.
because last time we were still kind of
Yeah.
figuring out
This is
delay
now,
issues.
you know exactly
Yes.
what we need.
Of course, we say
Until
that
the
until our.
next issue pops
All right,
up.
we're not even gonna
Yeah.
bother with going back to our screen again. We're just gonna get started, and then I'm gonna
Okay.
pause this
Look,
so that we don't have that extra.
turn off so my phone doesn't
Yeah,
die.
here you go. Yes.
Appreciate it, brother.
All right, guys.
Okay.
Well, I'm glad that we didn't disappoint and that
Yes.
we came here with a full suite of audio issues.
Oh yeah.
Once again. So, yeah.
Great. We prevailed.
Welcome to ThetaWave Podcast.
Hello, guys.
My name is Ryan Reed.
Mm.
I'm your personal machine learning expert. And I'm also a neuroscience researcher and a musician, songwriter. And I'm here with my co-host, Jacob Holland. And Jacob is also a neuroscience researcher, as well as a musician, as well as an actor. Man of many talents.
For you.
Do you want to tell us what we've got going on?
Yep. Okay. So we've got our machine learning topic today. I know it's not going to be the last part of the LSTM cells. That'll be for next time. This
Right.
one is going to be a really interesting one. It's how AI model performance is evaluated and visualized to determine optimal hyperparameter values for the purpose of improving model
Exactly.
metrics.
Yes.
Yes.
And we are the reason for this one was because I hadn't prepared for the other the enough for the other covering the other topic the last half of the LSTM cell. I still had to put together some visuals for it, and so that one wasn't really ready to go, and this one was really relevant right now because I was working on a model and had saved the metrics for it and was about to do that tonight, to dive into that in depth on my own. And I realized that might be actually kind of fun for us to do as our machine learning topic live and talk about what that is and why it's done and all that. So basically you are going to get a live view of me kind of working on this, delving into what it is, and what the things I'm looking at are, and kind of my thoughts as I'm looking through it, the metrics. And luckily for you, the metrics are not solely numbers. They are very colorful graphs.
Ooh, get some eye
So
candy.
yeah, you got some eye candy there. Nice squiggles and bars and whatnot. So we will go ahead and I guess dive right into that. I first want to start about talking about what hyperparameters are in a model context. Hyperparameters are parameters within a model that are not learned by the model. They're something that are set initially usually by the machine learning engineer. And you can think of them kind of like um like a temperature in regards to oven, like cooking something, You might have your recipe, which is going to get baked in a certain way. You have kind of a goal for it, the goal for it that you want, um, the outcome, but you've never made this recipe before. You're not following from an instruction manual necessarily, so you don't know exactly what that temperature is supposed to be, and the best temperature. You might have a general idea of what that's supposed to be at, but you might not have an idea of the best um, temperature
Yeah.
and how it's going to play out. So you make it too hot, not with too long a time, where time is another hyperparameter. Then it's obviously going to burn itself.
Yeah.
If you too cold, um, then you may end up having to bake it for a really long time and not end up maybe not even get the kind of the right rise out of the bread or whatever it is you're baking. Don't ask me how I know so much about baking.
He's also a
So
cook. You forgot to mention
what
that.
happens when you grow up with three
Yeah.
sisters. Um, but um, yeah, so you have these not only these settings that you set with for your model that control things like learning rate, that's a hyperparameter, right? As well as maybe if you have something called dropout included. Dropout determines how many of the neurons to cancel out and drop out, and so
So they don't get too biased.
that's a hyperparameter.
Yeah. Okay.
Exactly. Yes,
Mhm.
that's one of the was what dropout was built for. There's has more uses than
Yeah.
that, but that's what it was built for. And um, you have um settings for perhaps even um, optimizer stuff. There's just a lot of different
Mhm.
options that you have, and so imagine those in the context of baking, something like that, and it's making sense why that stuff becomes more and more complex because you not only have direct interactions with the outcomes,
Mhm.
you have secondary interactions
Mm.
with the outcomes.
Okay.
So you have interactions between settings. Like for instance, if we didn't know the relationship between temperature and time when cooking, like those two interact with each other, which then affects the outcome,
Yeah.
and they interact with each other
Mhm.
strongly. And so while that may seem obvious in the case of cooking, in the case of
Yeah.
hyperparameters, those kind of things aren't necessarily
Yeah,
so
those aren't,
obvious.
like, automatically synchronized. Okay.
Right. And so, as an example, actually we'll take a look and
Okay.
we'll see how that
Mhm.
that plays out. But so those are hyperparameters. Typically, like I said, those are things that machine learning engineers set up. Um, we do have automation tools for that kind of thing now, but still involves machine learning engineers setting up the initial boundaries, so to speak,
Yeah.
for those parameters or the options. And what this automation does, and this is what I used to um, gather the data that we're going to be going over. But basically, what I did was I set up a bunch of different potential options in a realistic range I thought the model might
Mhm.
benefit from, within these hyperparameters. So like, set the learning rate from something more along the lines of a faster learning rate to something more along the lines of
Yeah.
slower learning rate. And then we have, other parameters that I kind of set between their minimums and maximums, as well as different um, layer sizes. So like I made sizes of different neuron layers and basically set up all these options and then ran like 30 different training sessions of one epoch, which is one run through the data. And some people say epoch, I say
I've heard
epoch, but
epoch.
yeah, the one epoch through the data. And the reason I only do one, some people do more for those kind of things, but I'm dealing with a really large data set, so I don't need
Yeah.
more than one to determine how all these things are affecting it. And so do 30 of those, and basically every single run, what it does is it uses a Bayesian network to start picking different hyperparameters and attempting to determine what the what those relationships are starting to look like. Okay, so like I know now that this one seems to affect the output, but if I mess with this one, does that affect that one's effect on the output? And so basically it starts testing these different combinations of settings that I've given it the option to. And like, okay, well, let's do one run with a layer of 68 neurons, or sorry, 64 neurons and 32 for the second layer. Now let's switch those around and put 32 for the and then 68 rather than 68 and 32. And so switch those around, see if that affects it. Let's try maybe 128 neurons and see if, and this will layer, and let's see if that works. So it's like just testing out all these options that I've given it, and then watching the results that happen and recording it. And basically the goal of this is to get enough data to be able to start drawing conclusions about these interactions and these settings. And you might think, is this all this really necessary? Couldn't you just set it up with a good base, parameters, and just train it a lot, and then, have it compensate for, any inoptimization in hyperparameters? And the actual answer in many cases is no. Like, the hyperparameters are so important to the ultimate capability of a model that oftentimes you cannot achieve through extra training the accuracy you would be able to achieve if you were to tune those hyperparameters properly. So there, when I was doing an initial training of a Bayesian network that I was working on, I did an initial run of, or several runs. These are called sweeps that we do. That basically are multiple runs with different parameters. That's called like a sweep. But I did a sweep early on, and as kind of an example of how much that can affect it, at certain parameters, my accuracy was laughable. Like, it was really, really bad. Other parameters, I was getting around the same accuracy as I was getting when I trained it initially after I created it. The base parameters that I set for it. I was getting a similar accuracy to that with some of them. A couple of them, I was getting really, really good accuracy. And I was able to kind of instantly pick out which ones those were, and the commonalities there, and the metrics that seem to really play a huge part in the outcome of that model. And so one of the ways that we do this, and before just diving into the visuals, I'm going to just quickly touch on this, is through our chosen loss metric. If you remember back from when we discussed this, loss is essentially our talking about our evaluation, or our chosen way of evaluating how well or poorly a model is doing. Basically, how off is it from its target values, you know?
Okay. Yeah.
And you can imagine this is kind of an ambiguous thing depending on what data you're working with.
Mm-hmm.
If we're working with time series data, like that's going to be would seem like it would be a different metric for calculating what's considered off and how off it is than if we were dealing with image data, right?
Okay. Yeah. Yeah. Yeah.
Because an image might just have a small section that's slightly off in color in a lot of different ways. And if we were to evaluate it this way, it might seem like it was way off.
Yeah.
So we have these different ways of evaluating things. And depending on the kind of data that we're dealing with. And um, typically our primary evaluator of what metrics are most important is going to be based off of that primary loss function.
Mm-hmm.
We have secondary metrics that we track sometimes too that are things that are important to us to maybe evaluate individually from the loss and see how those are doing too, and maybe some of the parameters that are important to that. For instance, in a Bayesian model, I usually evaluate via something called Gaussian NLL loss, um, which is the primary loss function that I use. However, I use another metric um, called May, which is mean average error, um, to determine accuracy because the Gaussian loss, the Gaussian NLL loss is not specific to accuracy. It also includes certainty.
Mm-hmm. How much uncertainty the model has.
It's like an evaluation of both the uncertainty and how well the uncertainty predicts the accuracy, or is like matching up with the accuracy.
Mm-hmm.
And so it's not a good indicator of exactly how accurate your model is.
So if you had high loss, but also low uncertainty, that would kind of give you a clue that something's wrong,
Yes,
essentially.
exactly. So that Gaussian, NLL allows us to do is it allows us to find when those two things are diverging,
Mm-hmm.
and the closer that those two things get, the lower, so the higher the accuracy and the lower the difference between the uncertainty, um, and the accuracy, then that means that the better that metric is going to
Okay.
be. It's a combined metric, and so it
Mm-hmm.
doesn't tell us like how well those things are doing individually.
Yeah.
So using something like May, mean average error, mean, and what that really just means is like, say we're trying to predict three different values, right?
Okay.
Maybe we're trying to predict a stock price, a stock volume,
Mm-hmm.
and then the average price for that stock, you know,
Mm-hmm.
for the next hour or something. Those would be the three features we're trying to predict. What it's calculating, mean average error is calculating, is how far on average are all those three features off from the target
Mm-hmm.
three features. And so it's just averaging those differences, you
I see. Yeah. Okay.
know. And so it's one metric that's important to me. Another one that's important there is going to be the specific uncertainty metrics. So I'm tracking the minimum uncertainty in any prediction. So if we're in those cases of having three features that we're predicting, right?
Mm-hmm.
Um, in the case of those
Mm-hmm.
those three features, and for every prediction, what is the minimum, like what is the minimum uncertainty? So like maybe it's on feature two, that we have our minimum uncertainty for one run. Maybe it's on 3. It doesn't matter. It's what is the minimum uncertainty in any run. And then what's the maximum uncertainty in any run? What is the mean, the average uncertainty for the run? Those are metrics important to look at because it tells me, first off, what are there some features that I'm able to predict with high certainty on, for any given run? Are there some that are that I'm really uncertain about, and then C, on average, how certain is my model, about these predictions that it's making? And so those are all like things you might want to take a look at how hyperparameters are affecting in order to determine, okay, what's a good compromise here? Like maybe there's something that affects this one, the primary metric positively, but one of the secondary metrics negatively. So you might not want to choose to necessarily the best thing for the primary metric if there's one that's close, that's not as detrimental to the secondary metric, right? So that's kind of what our purpose is with those, is like to flush out all of this like really complex interactions,
Now,
and then
are we gonna look at how hyperparameters are actually set in when you're making the training program for the model? Because that would seem interesting to me to see, oh, this is actually what it means to set the hyperparameters, like the boundaries for it to train in. I think that would be kind of cool. Unless you want to, if not, then maybe you could say like what the actual settings look like in the program, you could say.
I could do that. It's kind of it would kind of be beyond a little bit beyond the scope of what we're going over, and might be a little unnecessarily confusing because it involves programming, and so they would have to know what the data structures are and like what even they were looking at there.
Could you give like a layman overview of like an intuition behind what a hyperparameter would actually look like in the training?
What do you mean what it would look like?
Look like as in the actual configuration of hyperparameters.
Okay. So typically hyperparameters are floating point values.
Okay.
Not always. Sometimes they're numbers. Like if I was creating a layer, a hyperparameter for a layer, um, like at the size, it might be a number, like 100 neurons in layer, or 64. Typically, we deal with things in 16s, 32s, like multiples of like 8, or 4, whatever you want to look at it. But that would be an example of an integer, but typically a lot of them are floating point numbers, which means decimal point number.
I see.
So learning rates are often something like 0.00001 or 0.00001, like, somewhere within that realm. And there are certain parameters that are there just for very micro like purposes. Like they're just really don't need to be messed with. Because they're just there maybe to prevent a specific issue, like a zero division or something like that,
Okay.
which can like computers don't like. They will flip out on you if you try to do that.
Yeah, that makes sense.
So they they'll add like a small number to something in order to prevent that from happening. And so that would be a potential hyperparameter, but one that doesn't really need adjusted because they make
Okay.
it so small
Mm-hmm.
that it's not really going to affect anything.
But a bigger one,
Would be something like the learning rate or the
okay.
dropout or the neurons, like
And
those.
that's the hyperparameters.
Mm-hmm.
I see. Okay, that
Yes.
makes sense. Sweet.
So yeah, that's let me see if I can figure out how to switch us over here real fast. Stream my screen. Can I replace it with a stream? Do that so that we can. Yeah, share screen.
Oh
Like
yeah.
that. Okay.
Sweet. Load. Here we go.
Find a place for this keyboard.
On the floor.
Putting it on the floor. Okie dokie. So we can see this okay, right?
Yep. Very nice.
So this is from a website called what I've always said it in my head, want to be,
One to be.
but I think it's actually one be or one to be, but I've want to be,
Sounds
but
better.
the it's weights and biases is what is the website or the company, and basically they made an online way for you to send metric information to their server, and then they'll basically take those metrics and provide a system for creating graphs and
Oh,
whatnot
that's
of it.
cool.
Yeah.
Nice.
So you still have to incorporate all of it into your code and like extract the metrics and whatnot, but they handle all the actual visualization of it to make it easier, which is really nice.
That is nice. Good for them.
Okie dokie. Let's see. Close down this cookie thing. All right. So as you can see, what we are looking at here is the sweeps that I ran on it, which is a sweep is a specific run, a training run on a model. Again, this was for one epoch because I did not need to do it for any more because of the size of the data that I was working with. Just the data size is so big that as I'm processing the data, pre-processing before sending it to the model, just means changing up the data and like doing some initial stuff to make it better formatted for the model. As I'm pre-processing this stuff, I had to completely redesign parts of the library that I built that I was using which was already an optimized library, but I had to redesign it to be able to handle the amount of data that I was working with.
Yeah.
Because it couldn't like load it all into memory. It was like running out of memory. And
Okay, change that a little bit. Yeah.
Okay. So let us look at
Evaluation.
what we've got here.
Okay.
So let me see if I can full screen this so that we have a little bit clearer of a view. Can you guys still see it?
I can see it.
You can see it? Okay.
Ooh.
Alrighty. So as you can see, we've got a colorful chart. Instantly, we can kind of determine what the best version of our model as far as our chosen metric goes, because it's right here. And this is what this means. We have our NLL loss that I was telling you about, our Gaussian NLL loss, right? So that is, but this means the val NLL is the validation phase NLL. Now that means that we are testing the model after it has been trained on a set of data that it has not seen yet, and we know it has not seen because we've reserved it. So we reserve a portion of the data for this phase, and we never let it see it, and then we will test it during validation phase on this data in order to get an potentially biased perspective on its performance. Because if we're testing it on data that it has seen, it's possible that those metrics could be skewed. So we just do that to avoid that. So we can instantly see what our best model is, which is going to be this one right here. And we know that because this particular metric is one that we look for a lower values on. The lower the value, the better. So if we go down here, let's not look up at the top one yet. Actually, yeah, let me change that back to where it was because I did change that unnecessarily to validation. You can see these are all the metrics that I'm tracking. Like these are a lot of them. My computer is struggling a little bit. Okay, that's it. You just type it in. What this does is it gives us a
Oh man.
what this does is it gives us a view over the different metrics or the different options that it's chosen and how those have ended up answering. So you see the coloring right on the end is based on the validations NLL value, right?
Okay.
So that calculation we do on those values. At the end, our kind of our loss function there is what we're using to determine where that line goes. And in this case, because we're looking for lower values, that means the further down on that line it is, the better. So we can instantly see if we scroll over one of those lines, like this one, which I believe is the best one there. You can see the parameters that it chose using that one,
Mm-hmm.
and kind of get an idea. Okay, like well, if I just wanted to see a good option without having any interaction further between them,
That would
that
be a
would
good
be a good one
choice.
to choose.
Okay.
Yeah.
Mm-hmm.
So you can also see kind of what the ones that were poor, and maybe determine based off that what it was that was causing them to be poor. So if you look at this one, you'll see. If we look at this one, we see that it had a dropout probability of 0.703. That's pretty standard. It has a H1 to 1 size, which means a hidden layer size for the LSTM of 256 and a distribution size of 64. That means those are just the number of neurons
Mm-hmm.
that are in there. And then L1 lambda, L2 lambda. You don't need to know too much about those, except those are very important things.
Okay.
Because, well, I mean, that's kind of a spoiler alert, but like the L1 and L2 parameters are something that can be incorporated
Mhm. I see. Mm.
256.
Yep. It's looking like perhaps it's the H1. It would be just based off of those two runs. I can see that it's probably the H1 size or the L1 lambda. And in this case, if I had to guess on those two, I'd say it's probably the L1 lambda that's causing that issue. But you can see, like, we can start pulling out these different metric comparisons and maybe guesstimating at like what is causing these kind of things. And we can get an even more detailed based off of the stuff that this website provides us. Because one of the things that they do, and this is really cool, is there was an approach to determine initially, one of the ways that these metrics were evaluated was via correlation. The problem with evaluating metrics via correlation is that their secondary interactions with each other are not always represented by the correlations. And so they do give us kind of an idea of maybe direct interactions, but they're not so good at determining overall, like, because you could have a secondary interaction that's very important, to another like hyperparameters interaction. So as a result, they basically do the method which involves, the technical way that it happens is involves training a random forest model on your parameters and your metrics in order to determine what is the most important parameter here. And it basically kind of disseminates and untangles all of that information of those secondary, interactions between hyperparameters. And it's not important to go into the details of how that works. I think there's a previous video we did on random forests, but just know that it does use a random forest in order to determine this, and it is very accurate.
Nice.
So we can see via that's indicated by the importance here, the importance. So we can see based off of that according to the random forest, the most important parameter to our chosen loss function, which is the NLL, is the L1 lambda. You remember a second ago when I took a look at those the runs that did really poorly, those orange lines, and was looking at it and was like, it could be one of these two things. It could be either that size, the I think it was the H1 size, or it could be the L1 lambda. And then I said, in this case, I think it's the L1 lambda. That would be my guess. I go up here and boom, sure enough, the L1 lambda is the most important to get right here. And because it has a huge impact on its accuracy. So with that in mind, an action I could already take on that would be like, okay, I'm going to do another run, this time just having it test out the L1 and L2 lambdas, like maybe just trying trying to get those
Mhm.
right, um, and that would give me a direction that I could go to even improving this further. But we can see here, secondary, by much less, but still important,
Yeah.
is the dropout probability.
Now, what
That
does
is
the
an
red
important one
in
to get.
correlation mean?
So correlation means that it has a negative
Yeah.
correlation, meaning usually the way that correlation is interpreted is that if I turn this up, like this thing up, then this metric also goes up with
Okay.
it. Negative correlation means if I turn this up, then that metric goes down.
Okay. I see.
Um, so again, direct
Mhm.
interactions. We're talking about if I do this, what happens
Yeah.
to this?
Mhm.
But it's not good at determining. Like, say, I turn this knob, and then this other knob is at this setting, and it goes up. But then I turn this other knob, and this one is at the same position, and now it goes down. Like, it's not determining
I
those like
see. Yeah.
relationships.
Mhm.
So that's why correlation is kind of like iffy
Yeah.
sometimes.
I see.
And okay, so um, interestingly, a random sampling size has very little to do with our end and all out.
Hmm.
Now you might think, what is that? Why is that important there? The reason that is interesting to me is that random sampling size is how many times we ask the model what it thinks with dropout, because this is a Bayesian network, which means that we want to get a lot of different opinions
Mhm.
from a lot of different sets of neurons in order to figure out what they all think the outcome is going to be. And then we take the mean of those opinions, and that
Mhm.
gives us our most optimal
Yeah.
prediction there, as well as the standard deviation between those opinions, which gives us our
Mhm.
uncertainty, right? So random sampling size is how many different opinions we get.
Mm.
And there's not a huge the random sampling size doesn't appear to be very important here to the outcome, which means I could ask for 10 or 20 opinions or 75
Yeah, it wouldn't
opinions,
affect it too much.
and it doesn't affect it a whole
Yeah.
lot, which is super odd. Um, there are a lot of potential implications. I might need to experiment with bigger sizes to see if I give it a larger range, if it seems to affect it more. But
Yeah.
uh, as I'm sitting here kind of thinking about that, the means that the neurons are pretty accurate across the board.
Mm.
It also could mean that they're a little too accurate across the board. In other words, there's not enough
Um.
variation between them,
Mhm.
um, which is just something to kind of mull through and consider, and
Mhm.
maybe try and determine if you need to run another version of that with a specific L1 and L2 set without varying it, because if you remember, those that L1 and L2 kind of help clamp those
Yeah.
variation between the neurons down. It keeps it from going too
Mhm.
far. And so maybe if we set those at the optimal value and then run another sweep just on the random sampling size and a couple other parameters, we would see more of an importance
Potentially. Mhm.
potentially, because we would be getting an optimal amount of variation between the neurons
Okay. Yeah, so
across all
that's
those
another
runs.
kind of example of how configuring something else can kind of impact maybe something that seemed like it was where it was supposed to be, because of this effect over here, you're gonna have to redo it a little bit. Okay.
Exactly. Yes. And we wanted to take it even a step further, which for many types of networks, looking at your loss, the impact on your loss is enough. You don't really need to look at anything else. But for this specific case, because this is such a complex network and there's specific areas you want to get optimal and right, that aren't always reflected by the loss function. We're going to take a look at other metrics to ensure kind of those are our optimal, kind of parameters and adjustments. So let me go down here and see if I can expand this a little bit. It's too small. No? Drag it. Hey, look at that.
Oh.
What are you doing? What are you doing? What are you doing? Stop it.
I'm in the middle.
Now let's expand it. Okie dokie. So we can see here, we are evaluating, just as an FYI, we're evaluating our validation may, which, as I explained earlier, is the mean average error. So according to our validation tests, these are the results from our mean average error there. Now we are taking a look at these different, and it looks like, okay, so first noteworthy thing, L1 lambda is still the most important parameter there.
Okay.
So that means that even both our accuracy and our NLL loss are dependent on that parameter primarily. And it looks like dropout is still number 2. And I don't know, I think L2 lambda. Yeah, that was third. Similarity between the May and the NLL. So let's check though, see what is important to our mean uncertainty, because that's another interesting. Let's see, low min uncertainty. Actually, I actually tracked the specific features themselves. So like the uncertainty across features. So I'm trying to predict, low, highs, opens, closes. Those features are things that I tracked individually as well, so I can see how things are affecting, and how each individual feature is doing. So let's go to train uncertainty mean. That's what I want right there. I think that's what I want. I don't think I tracked. Did I track? I might have tracked the val. Did I track the val? Come on, moving around on me, will you? Yeah. Let me just search for val here. Let's see what we got. Val. Okay, we got our val coverage, which no. Uncertainty, I guess, is what we're gonna go with. We're just gonna look at that right now. Interesting. Ah! Get it, squash it. Another bug. Okay. Interestingly, while our L1 is still the top there, our L2 now takes the secondary position. So L1 and L2 seem pretty important to predicting uncertainty. And H2 size, interestingly, is also seems to be important. And dropout is too further down the list than it used to be. And if we wanted to look at maybe our minimum uncertainty to see what's affecting that. On L2, dropout probability now takes third base in H2. So we can kind of like even break down these like specific areas and see if there's one area that we're really just specifically looking at trying to improve. We can kind of get an idea of the parameters we might want to take a look at and see how, and we could even do like a run, or we could check the parameters in correlation to, you check these, do this same graph in correlation to a different end goal. So if we were trying to see the parameters, run information here, like the results of each run. If we wanted to see maybe what could overview commonalities that were affecting the mean average error, or in this case, because they're kind of pretty correlated, we wouldn't look at that, but maybe the mean uncertainty, we could basically go through and edit the primary, where we basically create another one of these panels here that had the uncertainty, whatever metric we were trying to track there, as the last column there, in order to see like what metrics were influencing our uncertainty. Because in this context, our reason why we use NLL loss as opposed to trying to like minimize directly uncertainty or average error, we don't necessarily want to always be right. We just want to know when we're wrong.
Okay.
So we want our uncertainty to reflect the actual accuracy of our predictions. Yeah. That's why we train it on nano. Yeah. Anyway, hopefully that kind of helps give a little bit of better of an idea of kind of what goes into some of these processes in order to determine how things are doing.
Really interesting information, And I've done a lot of scouring on the internet for different podcasts or different lectures, series on YouTube, just about how machine learning engineers do it, how they actually train models and stuff. And this I really like because these visuals and your explanations paint a really clear picture into the actual details without becoming way too overcomplicated. It's like that really nice balance of like in between.
Yeah, it's important to like, I feel like when you're explaining something to somebody, it's important to be able to not use words that they don't know in order to describe words that they know.
Oh yeah, absolutely.
And in this case, we're already dealing with things that are so complicated and kind of, which is kind of funny because the actual task that we're having the machine learning model figure out is so much more complicated than even just these evaluations that we're doing, but it's still such a task to evaluate these things. And having an understanding of like what is going on in maybe in an engineer's mind, or like in the when a new model of something is released, and it's got better accuracy, the things that they might be taking a look at, or and in case of like really large models like OpenAI's ChatGPT versus
Yeah.
Gemini versus all
Totally
these
get
other.
that.
Um, I mean, they were not going to be
Mhm.
looking at this exactly, but they would because they usually have architectural changes in the models between them. Um, but typically they evaluate them on the same data sets, which means that they can cross-reference
That's how they
these.
okay.
Um, yes, and so they can basically, cross-reference like the different models' accuracies
Mhm.
here and determine what it's most accurate
Yeah.
on and how it compares to other models. They do a similar thing here to compare those
Mhm.
models together, um, as they would to kind of comparing hyperparameters.
Absolutely. Absolutely.
So yeah. Anyway, that is a brief look
Mhm.
into kind of the evaluation phase, the tuning phase of
Yeah.
machine learning model training. This has been very, very informative, a very informative Bayesian
Mhm.
sweep for me here. Um, just because, I mean, I changed up the format of the data going into it, and I wanted to see if that changed up the
Mhm.
hyperparameters, the optimal
Yeah.
hyperparameters that I'm using. So now I just need to go back to my previous hyperparameters that I did for the previous sweep and compare and see whether or not those are having a huge impact on
Yeah, you're gonna have to
accuracy or
update
not.
us on that. Absolutely.
Yeah.
All right. Really good stuff. I enjoyed that. I feel like
Yeah.
I came out of this learning something new.
More
Yes.
knowledgeable, more informed, and a better
Mhm.
individual.
I mean, what was that one software you sent me that was for like model training? That one kind of like software that made it like really easy to train models.
I know what you're saying.
Yeah,
It's been a
yeah.
long.
Yes,
Orange.
orange, orange. This is
Yeah.
kind of what it showed me in essence. And the first time I looked at it, I was like, huh? How am I going to use these numbers and apply them to, you
Mm.
know, make the hyperparameters for my model better? And I kind of scratched my head and played around with it. And I was like, oh, okay.
It was like
Yeah.
cool to see, but then you're like, I'm not sure what to
Exactly,
do
but
with this
now, like, after
information. Yeah.
this, I'm like, "Okay, now I kinda wanna go back and play with it some more now that I have a better understanding of how to actually evaluate
Yeah.
that information, that data." So
Yeah. I mean, and this information was all specific to the model that I'm
mhm,
running. Like, so there are a bunch of loss functions out there and like
yeah,
metrics that you can track for things. So if you're evaluating a unsupervised learning model, or if you were using a unsupervised learning model, which I'm thinking maybe if you were using Orange
there's both supervised and
out of the
unsupervised.
box, you might have been running
Mhm,
it unsupervised, but um, those metrics are going
yeah,
to be different and they're going to mean
mhm,
different things for the model depending on. So there's a lot of
oh,
learning
yeah,
involved in like figuring out
mhm,
are that you're looking at and how they indicate and what they
no,
indicate.
absolutely, absolutely. It's kind of like how you can think about learning different like aspects of mathematics for particular application, like computational modeling, for example. And then now that you actually know the equations and have like a almost like an emotional contact with that information, you can then translate it, associate it over with a, a different topic, but with the same kind of base structure. And that's kind of how I see
Right.
this. Where it's like I'm probably not going to be working with Bayesian models, but at least I know, yeah,
The
like, the
context there is
context is
still
huge
important.
and very
Yeah.
translatable.
And it like gives you an idea of the methodology, the different sections, even if the items themselves are changing,
Mhm.
like the loss function or the metrics you're
Yeah.
tracking or whatever. Like that's that stuff all may change, but the general process is the structure, the context, the why behind it. That stuff all pretty
Mhm.
much remains
Yeah.
similar, and so it can really help you gain an overarching understanding and then you can just fill yourself in on the
Exactly.
details,
Yeah.
Yeah.
Pretty awesome.
Awesome. Alrighty. Well, I think we'll call it there for
Mhm.
today. It's been a little bit shorter one, but we wanted to get a podcast in,
Yes.
and we weren't sure when we were going to be able to do it because this week
Pretty
was really
crazy.
busy. So we decided to do one tonight, and because of how late it was by the time we could actually get here to do it, we had to cut it a little short.
Yep.
So we will most assuredly, though, be back with more fascinating
Definitely.
concepts and
I think next week
discussions.
you should expect IDRA 21,
Yes.
the nootropic.
IDRA 20. Very interesting.
Mhm.
I don't want to spoil anything,
No
but
spoiling.
um, it has a couple of very interesting properties.
Mhm.
One of which, how
Yeah.
long,
Mhm.
is very unusual. So we will delve into that next time.
Yeah.
Yeah.
Thanks for
Anyway,
watching.
thank you guys for watching so much. We will see you in 4, 5, 6, 5 days. 5 days. Tuesday.
Yeah.
Right.
Mhm. Tuesday.
Cool.
Sweet.
And be on the lookout too for maybe some smaller videos too. I've been trying to get my motivation up to post some smaller.
Mhm. Yeah. You should expect the hypothalamus video to be uploaded in the next 2
Cool.
days or so.
Awesome.
I'll
Awesome.
say.
I'm assuming that's
Mhm.
from you because it's not from me.
Yeah, that's from me. Sweet.
Awesome. Alrighty, guys.